Hey, hi, this is Joel over here, and this is the first video of our NLP course. And NLP, in the sense, it's called Natural Language Processing. So, what is natural language processing? We have to process the natural language which we, the humans, speak, and we have to make the computers to understand the language which humans speaking. Basically, computers understands zeros and ones, and we have to make computers understands the language which we speak into zeros and ones and make them to interpret and compute and gives us a proper results. So natural language refers to how people communicate with one another, and humans regularly communicate in many different languages like English or any other regional languages. So those languages should be converted into ones and zeros such that computers can understand and they can react intelligently to communicate to the humans. So this is called the overview of natural language processing. Natural language processing is a subset of artificial intelligence that enables machines to understand and communicate natural language like humans does. It also involves using algorithms and techniques such as machine learning, deep learning, and text analytics to interpret and analyze natural language content from audio recordings, document, images, or other sources. And applications of natural language processing. So natural language processing, so NLP can be used for sentiment analysis, chatbots, online searches, document analysis, smart assistants, and automatic summarization. And there are various kinds of applications for NLP. Let's see like one by one in later. And Google Translation is also one kind of NLP application. Microsoft Copilot, Bing in NLP, and all these are like kind of major applications that we are using in day-to-day life with NLP. Computational linguistics. So, what exactly is computational linguistics? It is the field at the intersection of language and computer science. In simpler terms, it's all about teaching computers to understand, interpret, and even generate human languages. It combines linguistic theory with machine learning and programming to create tools like chatbots, speech recognition system, language translators, virtual assistants like Siri or Alexa, and even grammar checkers like Grammarly. It's the brain power behind how machines make sense of human and communicate. So why it matters? Computational linguistics helps solve real world problems like breaking language barriers, enabling voice to text technology, and even analyzing social media trends. It's also key in developing natural language processing, which lets AI system reads and responds like humans does. Without computational linguistics, modern AI would have no clue what we are saying or typing. And history of NLP. So NLP is basically got generated in 1950 by a famous person called Alan Turing. And the first article for NLP has been titled called Intelligence, and which has been proposed now called as Turing test. And based on the famous experiment, which is like Georgetown experiment, which happened in 1954, it fully involved in automating translations of more than 60 Russian sentences into English. And in 1980s, most of the NLP systems were being based on complex sets of handwritten rules, which doesn't have any deep learning or machine learning. It's full of handwritten rules. And in 2010, deep neural network has been initiated, and machine learning methods became widespread in natural language processing. And this is a short history of NLP. Let's understand the processing stages in NLP. We have 7 processing stages in NLP, and they are phonological analysis, lexical analysis, syntactic analysis, semantic analysis, discourse integration, pragmatic analysis. So let's go one by one. What is phonological analysis? This is all about sounds. When we speak, we produce various sounds like phonemes. Phonological analysis is used especially in speech recognition system, like when you ask your phone to call someone or search something using voice. Here, the computer breaks down your speech into phonemes and tries to understand how those sounds combine to form words. So basically, it answers what sounds did the person just make. And the second is morphological, or you can say it is as lexical analysis. So morphological analysis, which is also called as lexical because it step focuses on structure of words. It splits sentence into individual words, identifies the root forms and checks for morphemes and the smallest units of meaning in a language. For example, the word unbelievable has three morphemes, which is un, believe, and able. At this stage, the system also looks up words in the lexicon or vocabulary to see if they are valid. It's like asking, is this a real word? What does it mean? What part of speech is it? So these aspects comes under the topic called morphological or lexical analysis. And the third we have syntactic analysis. So syntactic analysis is also called parsing. This stage checks the grammar of the sentence. It builds a tree-like structure to show how words relate to each other. For example, in the sentence, the cat sat on the mat. The system identifies the subject, the cat, the verb sat, and the object on the mat. If something is grammatically incorrect, like sat the cat mat on, the syntactic analysis would flag it as a problem. It's all about making sure that sentence structure is correct. Semantic analysis. So now the system understands the words and the grammars. It tries to understand the meaning behind the sentence. Semantic analysis looks at the context and relationships between the words. For example, she unlocked the door with a key. It understands that the key is a tool used to unlock something. It also detects ambiguity, like a sentence which we say, I saw the man with the telescope. Did I see the man using a telescope? Or did the man have a telescope? Semantic analysis helps to figure that sometimes with the help of the next step, which is discourse integration. This is where the machine looks beyond just one sentence. It considers context across multiple sentences to maintain coherence. For example, John went to the store. He bought some apples. Discourse integration helps the system understand that he refers to John. This step is essential for chatbots, personal assistants, and language models to carry on meaningful multi-tone conversations. Finally, we have pragmatic analysis. This step focuses on the intent behind the words because sometimes the literal meaning isn't enough. For example, if someone says, can you open the window? They are probably not asking if you are physically capable. They are politely asking you to open it. Pragmatic analysis understands these tone, sarcasm, commands, and even hidden meanings based on the situation. It answers what does the speakers really mean. This is especially important for AI systems to interpret human emotions, politeness, commands, and real world knowledge. So, in summary, phonological analysis is used for recognizing sounds, lexical analysis, identifying words and meanings, syntactic analysis, checking grammar structure, semantic analysis, understanding the meaning, discourse integration, maintaining context across sentences, and pragmatic analysis, interpreting intent and implied meaning. Each step builds on the previous one, forming the backbone of how machines understand human language. So next time you talk to Siri or Alexa, just remember they are running through all these steps in milliseconds to reply to you. Now we are going to talk about computational linguistics. So what is computational linguistics? Computational linguistics is a branch of linguistics that uses computer science and algorithms to analyze and understand human language. It's the science behind how machines read, interpret, and generate natural language. Unlike programming languages, which are clear and unambiguous, natural language is messy. For example, the word bat can mean a flying mammal or a sports equipment. This is called lexical ambiguity. One core goal of computational linguistics is to resolve this ambiguity so that machines can understand what we really mean. Let's talk more about ambiguity because it's the biggest challenge in language processing. Let's consider the sentence: I saw the man on the hill with a telescope. Now, did you see the man using a telescope, or was the man on the hill holding a telescope? This kind of structural and semantic ambiguity makes it hard for machines to interpret meaning unless we teach them to disambiguate. That's it. To figure out the correct meaning from the context. Natural versus programming languages. Programming languages like Python or Java are precious and have strict rules. Every command has only one meaning. Natural languages like English are ambiguous, flexible, and filled with exceptions. Computational linguistics helps bridge this gap by creating algorithms that can understand human-like language in a structured, computer-friendly way. Levels of ambiguity. We have four levels, which is lexical ambiguity, syntactic ambiguity, semantic ambiguity, and pragmatic ambiguity. Lexical ambiguity. Let's consider the sentence: the fisherman went to the bank. Is it a river bank or a financial bank? Ambiguity exists over here. Syntactic ambiguity. Visiting relatives can be boring. Are you visiting them or they are visiting you? So syntactic ambiguity exists over here. Semantic ambiguity. The teacher said on Friday she would give a test. Did she say it on Friday or is the test is on Friday? Again, ambiguity exists over here. Pragmatic ambiguity. Can you pass the salt? It's not a question about ability, it's a polite request. So, resolving these ambiguities is key to making NLP systems more accurate. NLP tasks and what computers needs to know. To process language, an NLP system must understand phonology, morphology, syntax, semantics, pragmatics. As I said earlier, phonology is the sounds of speech, morphology is the structure of words, syntax is the grammar and sentence structure, semantics is the meaning, pragmatics is the context and intention. Computers need to integrate all these layers just like humans do when we speak or read. Empirical laws and word frequencies. Here where computational linguistics gets mathematical. You ever heard of Zipf's law? It says that in any large text, the most common word appears twice as often as the second most common, three times as often as the third, and so on. For example, in the Mark Twain's Tom Sawyer's, words like the and of occur far more often than content heavy words like fence or paint. This tells us a lot about language patterns and helps NLP system prioritize important words. Content words versus function words. Let's break language down into two parts: content words and function words. What are content words? Nouns, verbs, adjectives. These carry meaning. Example, daddy play ball. Even with minimal grammar, the meaning is clear. And for function words, prepositions, conjunctions, articles, they hold the sentence together but don't carry much meaning alone. Computational linguistics often filter out functions words during processing to focus on the key content. Type versus token. Here's the fun concept where TTR, which means type token ratio. Tokens are total number of words, types are unique words. Let's consider the sentence. The quick brown fox jumps over the lazy dog. The dog barked loudly. So tokens, there are 13 total words, which is the quick brown fox jumps over the lazy dog. The dog barked loudly. So there are 13 total words, and the unique words are the quick brown fox jumps over lazy dog bark loudly. So there are 10 total words. So 10 divided by 13, it's approximately 0.769. So the final TTR value is 0.769. A higher TTR means more diverse vocabulary. A lower TTR means more repetition. This is a super helpful in analyzing speech patterns, language learning, or even writing style. And real world applications. So where is it computational linguistics are being used today? Chatbots like ChatGPT, voice assistants like Alexa and Google Assistants, translation tools like Google Translate, grammar checkers like Grammarly, search engines like Sentiment Analysis, and more. Let's begin with Heaps Law, an important statistical observation in language processing. So what is Heaps Law? It tells us that as number of words in the document increases, the number of unique words also increases, but at slower rate. It is expressed as V of n is equal to k into n power beta, where V of n is the number of unique words, n is the total number of words, k is the constant, usually around 10 to 100, and beta is the value between 0 and 1, typically between 0.4 and 0.6 for English. In simpler terms, the more you write, the more unique words you will use. But after a point, new words show up less frequently. Most of our vocabulary is made of repeated common words. So let's consider an example of Heaps Law numerical. So here they have given a vocabulary growth of Jane Austen novel. So it has total words which is n and distinct words which is v of n. And total words are 10,000, 50,000, and 1 lakh. And distinct words are 2,000, 5,000, and 8,000. So as a first step, we have to find log of n and log of v of n. So log of 10,000 is like 4, and log of 50,000 is 4.7, and log of 1 lakh is 5, and log of v of n is 3.3, 3.7, and 3.9. So once this log transformation has been done, step 2, we have to calculate the slope, which is beta. As we know, log of v of n is equal to beta into log of n plus log of k. And the formula for beta is equal to n into summation of log n into log of v of n minus summation of log n into summation of log v of n divided by n into summation of log n square minus summation of log n the whole square. So the values have been substituted over here and we found beta is equal to 0.595. Now it's time to calculate the intercept, which is log of k. So log of k is equal to summation of log of v of n minus beta into summation of log n divided by capital N. So capital N is the total number of rows that exist in the numerical table, and we have 3 over here. So all the values has been substituted, which is 10.9 minus 0.595 into 13.7, which we get approximately 0.916. So K is equal to approximately 2.5. Inferences from Heaps Law. Here are some key insights from Heaps Law. Vocabulary growth, language complexity, empirical fit, K as a scaling factor. Vocabulary growth. New words keep coming but slower over time. Language complexity. Natural language has a lot of repetition. Common words dominate, but occasionally unique words still add richness. Empirical fit. Most English texts fit well within Heaps' expected beta range of zero point 0.4 to zero point 0.6. K as a scaling factor. Higher K means more unique words early on in the text, useful to compare authors or genres. So, applications of Heaps law. So, where is Heaps law being used? It's been used in linguistics to study vocabulary richness and compare different text or writers. Search engines like helps optimize indexing and estimate storage needs. Text analysis like editors and researchers use it to evaluate writing style and content complexity. It is a powerful tool that helps both machines and humans understand the richness of language. Turing test. Now let's switch gears to one of the most iconic concepts in the AI, that is the Turing test, the named after Alan Turing. The Turing test is a benchmark used to test machine intelligence. So how it works? A human judge chats with two participants. One is machine, the other is human. The communication is text only with no visuals or audio cases. If the judge can't reliably tell which is machine, the machine is said to have passed the Turing test. That's huge. It means the machine has shown human-like intelligence, at least in conversations. But passing the test is not easy. To succeed, the machine must understand natural language, reason logically, use contextual knowledge, respond like a person. Think of smart chatbots, AI companions, and virtual assistants. They are all trying to get closer to passing this test. Even today, the Turing test remains a symbol of intelligent behavior in machines. But some AI systems come close, very few can consistently fool a human judge. It's not just about grammar, it's about understanding emotions, context, and intent. So that's it. This is the end of our first module in NLP, which is natural language processing. Hope you guys understood well. Thank you.